Now that we've seen how our unconditional go-to instruction works, let's take a look in more detail at one of our conditional jumps. And so the one that we're going to focus on in detail is this if less than. And so as we can see in the description, this is popping a word from the stack and branching if it is less than 0. There are two other conditional branch instructions. So we have if equal, which is popping a word from the stack and branching if it is 0, and also if icomp equal, which is popping two words from the stack and branching if they're equal. So again, we're going to focus on this middle one right now, but all of the things we're going to talk about are going to be very similar for the other two. And so of course, remember this table of our ISA level instructions can be found on page 4-16 in Canvas. So one thing that we note is similar to the unconditional branch that we talked about previously, our go-to instruction, all three of these conditional branches also have an offset, and each of those three offsets is 2 bytes or 16 bits. And so what that means is we have assigned 16-bit values. So we have 2 to the 16th different possibilities. Because it's signed, it's split around 0. So we have anywhere from negative 32,768 to positive 32,767. And again, what that number represents is that's the offset we're going from the start, the program counter at the start of our instruction, right? So we can actually go to instructions that came before or instructions that came after, and these are the ISA level instructions in our method area. But just like the go-to instruction, again, this offset is from the start of the instruction. So it's not from where our PC currently is, but where our PC came in sort of at the beginning of that instruction, in this case, the conditional branch. So like we have been doing all along, let's start by looking at our ISA level instruction stream. So ISA level instruction stream, and again, of course, these are bytes that are being read into our MBR. They are bytes that are pointed to by PC, and these ISA level instructions are stored in our method area. So just like with the previous go-to video, we have 3 bytes here. So the first one is going to be our if less than. So we'll put IFLT, and of course that's going to have some hex code that we can get from this table. So we see that is hex 9B. So if LT is hex 9B, so we'll put that down here in parentheses. So hex 9B. And then we'll have, just like we did for go-to, we'll have some offset byte 1 and some offset byte 2. And just like for our go-to and every other micro instruction sequence we've considered, of course, we'll have instructions that come after that. We'll have instructions that came before that. And so now let's consider sort of the specific sequence of micro instructions that accomplishes this if less than, this conditional branch. And so looking here, we can see that we actually only have 4 micro instructions or 4 cycles. So 4 micro instructions or 4 cycles through our data path, but that's only looking at that if less than. What we're going to see in a little bit is depending on whether or not we branch, we're actually going to end up using our unconditional branch to go to where we want to. But we'll get to looking at that here in a second. We're also going to want to keep track of our program counter. I'm not going to keep track of it in registers explicitly like we did last time, but that's something important to keep track of. And so as part of that, let's also, like we've done before, write out our main one here. So we've got our main one is going to be PC equals PC plus 1, semicolon, fetch, semicolon, go to, parentheses, MBR. And so, of course, initially our MBR, if we have this IFLT instruction, it's going to be this 9B, which was loaded in whatever instruction came before main 1. Well, actually 2 before main 1, right? Because we have some delay for our memory read. So that would have been fetched 2 instructions before main 1. That's what's in our MBR here. So that's going to cause us to go to this IFLT 1. We've also incremented the program counter, so now our PC is pointing to the offset byte 1, so let me go ahead and indicate that here. So this is our PC, so again, that's because that got incremented right here, and we've initiated that fetch because we're going to need that eventually, or in this case we might not, but more often than not we'll need it, so we can go ahead and initiate that fetch. Again, that's going to be ready 2 cycles later, that fetch, so because we're going down here to T1, so that's going to be available in IFL T2. So we'll say this is available in our MBR at that time. But now let's come down here to our IFL T1 and see what's actually going on. So we can see we have some operations. So we have SP minus 1. And the reason we're dealing with our stack pointer, SP, which is pointing to the top of our stack, is coming back up here to what this operation is doing. Right here in this line that's already highlighted is we're popping a word from the stack. So regardless of whether we branch or not, we're taking this top word off of the stack. We're then doing some comparison with it. And based on that comparison, we're taking one of two paths. So the first thing that we're doing then is we're decrementing the stack pointer. We're then updating our SP and we're updating our MAR. The reason that we are setting our MAR to SP minus 1 is remember that typically in our TOS register, we're going to be storing the current top of stack value. Well, we've just adjusted what our top of the stack is, so we need to update that register. So setting the MAR equal to that address where our new stack pointer is sort of setting us on the road to that. And sure enough, we can see we're initiating a read here. And so that read, of course, isn't going to be available until 2 cycles later. And so that memory sort of lag, of course, we've mentioned several times, and that initially was talked about on page 4-6. So coming back over here, we can say this is available. And of course that, because that was initiated by MAR, that is going to be available, the data, in our MDR register. All right, so we've decremented the stack, we've initiated that read, and what we do next in our IFL2 is we have OPC equals TOS. And so what we're doing here is we're actually using OPC a little bit differently than what we saw in the previous video with Go2. Here our OPC is just being used like a scratch register. So let me draw an arrow down here, and so let's just say we're using this as a scratch register. And so the reason for that is, of course, remember what we're doing with this if less than instruction is we're popping the top word from the stack. We want to be using that to compare something, or compare that to 0 and then doing something based on that comparison. Well, of course, we don't need to read that because that value is already in our TOS register. But we see in the next instruction, we're going to be updating our TOS register because we are updating our stack pointer. So we need to put that somewhere so we can use it in a little bit. And so that place that we're going to put that temporarily is our OPC register. So we've got that in our OPC register. What we do then in our next micro instruction, our IFL T3, is we're saying TOS is equal to MDR. And so all this is we're just updating our TOS register, right? So we decremented our stack pointer. So now we need to have a new TOS in case we need that later on. And again, like we said, sort of at the start of when we were looking at these micro instructions, is that TOS register, having that top of stack value there sometimes can save us a memory reference, which means that we can operate our programs quicker. So we want to make sure we keep that up to date. The next instruction, what we're doing is we're saying we're taking in, and so remember in was sort of one of our extra registers we added towards the end, so our N and Z, and basically what that N equals OPC is doing is it's going to run the OPC, so it says running OPC through our ALU, and it's going to set our N and Z flip-flops. So running OPC through the ALU, and we'll say in parentheses, not storing it back anywhere, not storing anywhere from our C bus, but it is going to set our N and Z flip-flops. And so remember we talked about in class, technically we could say Z equals OPC, and that would still set our N register, but technically not great practice. So it's better if we just set that equal to N because that's the flag we're interested in. And of course we're interested in N because that's for negative. So we're passing this OPC, which was our old top of stack value, through the ALU. If that value is negative, of course, that means it's less than 0, which coming back up here to the top, that's what we're ultimately checking for. So we're passing that through the ALU, we're setting our N and Z flip-flops, and then the next part of this IFL T4 is we're saying if it is in, so if it's negative, we're going to go to some label T, else go to F. And as it says here, we're basically just branching on our in bit, right? So we have one of two possibilities. So let's consider the simpler of the two first, which is going to be this go to F. So if we go to F, that means our negative flag was not set. That means our value in the top of the stack was positive, which means we do not branch. So if we do not branch, we're going to be coming to F. So let me change that back to my pen. So here is where we come if our branch condition is not met. So if branch condition is not met. And so what we can see in our F is the F at the very start is we're just incrementing our PC. So we don't do a fetch or anything like that. So all we're doing is we're taking this PC and now we're putting it over here. In the next line, we're incrementing that PC again, but now we're incrementing a fetch. So coming back up here, what we can see as we increment that is now we're pointing to the instruction that comes after the offset. So we do want to fetch that in. And of course, that's going to be available 2 cycles later. And that next cycle, as we can see, is going to be our main one. So available in our MBR. And then of course down here, because we are in our F3 going to main 1, the instruction that comes after this is going to be our main 1 line, which I've written up above, of course. So that's the same main 1 that we have here. And so then we're just going on and we're doing whatever instruction came after that branch instruction. So we did not take the branch. Let's sort of go back in time and let's say instead of that situation, maybe now we do have that branch condition met. So our OPC, which was our old TOS, is negative. So our in flag got set. So now we're going to our T label. So this point right here is where we come if our branch condition is met. So come here if branch condition is met. And so we can see, let me sort of reset my PC as well, right? So initially our PC was set to point at the offset byte because of this PC plus 1 that we had in main 1, and it was just sitting here throughout our time in our IFLT 1 through 4, right? Nowhere in there did we adjust our PC. So now we come to T, and so what we see here is we're saying our OPC is equal to PC minus 1. So basically our PC is now pointing to offset byte 1, and we're setting our OPC equal to whatever this address was for the start. And so the reason for that comes back to where we were talking about the offset is this from the start of the instruction. So we set our OPC, and here we're using the old PC register the same way we did in our go-to instruction. This is holding our old program counter. And the other part of this instruction is now we're just saying go to 2. So from here, basically what we're doing, and let me do a different color. So from here, we're coming back up to go to line 2. And so what we notice is that go to line 1 is actually the same thing that we had done down here in the T. So essentially, we've just initiated a go-to sequence. And we've initiated that go-to sequence with our offset byte, or our 2 offset bytes that came as the operand for this statement. So from there, as we go through our go-to sequence, it's the same thing as what we looked at in the previous video. The main difference is, of course, we don't always go down this road, right? If that condition wasn't met, then we just keep moving to whatever came next in our instruction stream. If that condition was met, we look at this offset byte, and then our PC is going to be jumping either really far, well, not necessarily really far, but it's jumping somewhere later, or potentially it's jumping somewhere before, because again, remember that that's a signed value. So that is how our conditional branch would work. And again, let me mention that it is very similar for our 2 other conditional branches, our if equal or our if I comp equal. A couple other things that I want to mention. One thing that we've talked about a couple places before, and so let me change back here. So we actually talked about this on pages 422. So pages 4-22 and page 4-11 in Canvas is that the addresses for our T and F in the control store can only differ by their most significant bit. So addresses for the T label and the F label in our control store. And so remember, our control store is what is holding our micro instructions. So in our control store can only differ in the most significant bit. And the reason for that goes back to, like we saw initially when we were talking about our N and our Z and how we can jump Z or jump in our microarchitecture, right? We said that only affects our most significant bit. So that restriction carries through into how our micro instructions are organized in our control store. So that's an important thing to keep in mind. And so ultimately it's up to the assembler that's assembling our MAL instructions, our microarchitecture language instructions, to assemble that appropriately in the control store. The one other thing that I want to mention in passing is, of course, we have a handout in Canvas and in class that I gave you, which has the full micro program. And so that can be found on pages 272 to 274 in the textbook, or again, it's on Canvas. And this has all the instructions that we've gone through in these videos and in the notes, as well as some other ones, and a couple other important ones that I want to point out, but I don't want to go through in detail, is our invoke virtual and our return. And so, of course, we had talked about these previously in the class as well. And so that was on pages 4-17 and pages 4-18 in the notes in Canvas. And it was a little bit difficult to talk about some of the things. The nice thing about these sort of step-by-step micro instructions is now we can more clearly see exactly what's going on. Of course, it's a little tedious to sort of track through all of these, but if we wanted to, we could go through, we could see exactly what's going on. Another thing to point out too is note that there are 22 micro instructions for our invoke virtual. So this is by far the longest of any of these sort of functions that we have. And of course, we could come back up here to our ISA level instructions. And of course, we do have here our invoke virtual and our iReturn. So these are included here. So again, we're not going to go through these in detail. The main thing I'll say is just remember it was important as we are invoking virtual to store our old address information so that we could sort of restore the state of the stack when we return from that. The last thing I'll mention is if you're looking on pages 274 to pages 282, so pages 274 to pages 282 in the textbook, there are some more examples, more descriptions of some of these sort of instructions, the ISA level instructions, as they're broken down into the micro program. So that could be another good resource as you're trying to get more comfortable with some of these micro instructions and this micro program.